Okay, well, let's go ahead and kick this off. Thank you, everyone, for joining us today to learn about the challenges and promises of microbial fuel cells. Um, we'll be discussing how microbial fuel cells have evolved over the past 100 years and why earlier attempts to commercialize them weren't successful. We'll also look at the best applications and future development that will broaden the commercial application. Today, I'm joined by the two co-founders of Aquacycle, Oriana Brechker and Dr. Sofia Babanova, CEO and CTO. Aquacycle is a water technology startup founded in 2016 with a mission to provide cost-effective solutions for the world's most challenging wastewater issues. Oriana is the CEO at Aquacycle and brings a diverse background of physics, astronomy, aerospace engineering, and material science. Her research on microbial fuel cells has resulted in 32 journal publications, 3 book chapters, and 8 patent filings. Sofia is CTO at Aquacycle and brings a broad expertise and experience in analytical chemistry, electrochemistry, biochemistry, microbiology, and material science. She has 12 patent applications, and her research has resulted in 48 journal publications and 1 book chapter. And I have to tell you guys, every time I talk to these two ladies, I learn from them. So I hope this will be a very informative and educational hour. And before we get started, I'd like to take a quick poll just to understand what your current experience and knowledge of microbial fuel cells are. So I'm going to launch the poll and then we'll get started. Okay, I'll close it in 5 seconds. And let's see how we did. So it looks like overwhelmingly, 61% of you says great potential, but not sure how well they can scale or be cost effective. And then 26% don't know much about them. So the good news is for Sofia and Oriana, nobody said they don't work. So really excited to see that was at 0%. And let's see definitely how the two of you can help people to understand on these two issues around how they can scale and be cost effective. With that, I'm going to turn it over to Sofia. And Sofia, go ahead, kick it off to you.
Thank you, Julie. So before we go into the topic of microbial fuel cells, I would like to explain what a fuel cell in general is, since microbial fuels are technically fuel cells. They're not that black magic as you think of. So what is a fuel cell actually? And a fuel cell is an electrochemical device that can transform chemical energy into electricity. So how this is done? There are a couple of components the fuel cell has. There is an anode, where an oxidation process occurs. There is a cathode, where there is a reduction process. And we many often have a membrane to separate the anode and the cathode. So a fuel, in this case is hydrogen, comes into the fuel cell. It has been oxidized at the anode by inorganic catalyst, releasing electrons. So these electrons travel throughout an external circuit to the cathode, where it's coupled with oxygen reduction reaction in most cases. So then what is a microbial fuel cell? A microbial fuel cell is a fuel cell, as I mentioned before. It has exactly the same components. It has an anode, it has a cathode. Sometimes there is a membrane, sometimes there is no membrane. But the main difference within these two devices or technology is that instead of inorganic catalysts, we have bacteria that are present either at the anode or the cathode that are facilitating the oxidation and reduction processes, which makes microbial fuel cells bioelectrochemical devices. But they can still transform the chemical energy into electricity. In the case of microbial fuel cells, though, the fuel that comes into the cell is not hydrogen, It's somewhat kind of organic. It can be a pure organic such as sugar, glucose, fructose, or acetate, or it can be something more complex such as wastewater. But MFC can generate electricity from any form of biodegradable organic matter. And then since we are oxidizing this organic matter at the anode, we are removing these organics from the wastewater. Oriana, can you please go to the next slide? Thank you. So this makes MFCs extremely suitable for wastewater treatment. There are other bioelectrochemical devices similar to MFCs, sharing similar concept, having similar design features, which are microbial electrolysis or microbial electrosynthesis cells. But despite MFCs, they transform the electricity into chemical energy. They also use bacteria either at the anode or the cathode, but the final goal of these devices is to produce value-added products, such as hydrogen or methane or something else. So what is the secret behind these bioelectrochemical devices? Why they can do what we are saying that they can do? And the reality is that nature created these special bacteria, special microbes that are able to perform the so-called extracellular electron transfer. So they consume organics to gain electricity. They oxidize these organics within the cell body. They release electrons, but these electrons do not stay inside. They actually travel through the cell membrane outside of the bacterial cell. And they reach this sole electron acceptor, which in nature is some kind of mineral like iron oxide or manganese oxide and so on, and they respire. And that's how they gain energy in nature. We take advantage of nature and we replace this mineral with an anode surface. So bacteria do exactly the same thing. They consume the organics, they release electrons, perform this extracellular electron transfer. But this time, we capture these electrons at the anode, transfer them to the cathode to generate electricity. So we are constantly pulling away energy from bacteria during the oxidation process. And by doing that, we are accelerating the bacterial metabolism. So these are microbes that are constantly on a run. They have to consume the organics faster. They have to consume more organics in order to gain some energy for themselves. That's why MFCs, when applied for wastewater treatment, can do it faster than any other, than traditional wastewater treatment technologies. So there has been a global interest in MFCs throughout the whole world. It's like almost every continent, there are many research groups that work on microbial fuel cells for many years. And the idea or the concept of microbial fuel cells has been discovered in 1911 by Professor Potter, who first came up with the idea of using microbes to produce electricity. But the research activity didn't pick up until the early 2000s, and after which we can see an exponential growth and scale of the interest and the number of publications within that field. And the reason why this happened around the year of 2000 is because MFCs were recognized as renewable energy source. Since they can generate electricity from any form of organic matter, they are perfect as a renewable energy source. So many researchers started working in that area. That's how I was introduced into microbial fuel cells as well. But along the way, some hurdles and challenges has been faced. Some theoretical limitations has been recognized, and slowly the interest moved from renewable energy source into wastewater treatment solutions, since we are removing the organics from the solution. So around 2008, that was the main focus on MFC research. And there were a couple of commercial efforts within US and Israel trying to commercialize the technology that didn't prove to be very successful, but that didn't stop the research interest in that area. And Aquacycle started in 2016, and 2017 was the first company who managed to commercialize MFCs for wastewater treatment application. So what made MFC so exciting over the years? I mean, we can generate power, that's great, from any organic matter, which means we can treat wastewater, that's even better. They can be used as biosensors to study what is the health of microbial community, be used in other wastewater treatment applications, and MFCs can be used in space to recycle the waste products, the wastewater, and generate power. But despite these exciting features, people shifted their interest from power generation into wastewater treatment. But what Aquacycle is actually trying to do is to take these both advantages and develop self-sustainable wastewater treatment solution. So what happened? Why in the year of 2020, there was a decline in the number of research publications? And there are a couple of answers. First of all, there was COVID. And second, many research groups try to scale up these devices, and that proved to be very, very challenging. In addition to that, around 2018, the research interest shifted towards microbial electrosynthesis cells and using microbes to synthesize value-added products. But we are going to talk about scalability more in this webinar. Why scalability was such a big issue, and it was so difficult to scale these devices into real technology and apply it in practice. And the reason is that dual nature of microbial fuel cells. As we said, they are bioelectrochemical devices. So they have these electrochemical component. So do we scale them as electrochemical devices, or we use the biological component for wastewater treatment and we scale them up as anaerobic digesters, for an example. So we'll go through the differences between these two approaches and what are the limitations that researchers faced there. So if we think about MFCs as electrochemical devices, as I mentioned, they are fuel cells. As fuel cells, they require certain aspects to be met, like minimal distance between the anode and the cathode. There should be a membrane to separate these two electrodes since they're so close to each other. You have to have a very effective catalyst to produce enough power. And of course, one fuel cell cannot provide enough to power anything. So you have to have a stack of those. So we'll go through all these different aspects. Let's talk about minimal distance between anodes and the cathode. So the requirement about that is that in order to minimize the electrical losses, the anode and cathode needs to be close to each other. But when you're talking about wastewater treatment, that makes this sandwich required structure not very applicable because wastewater has high solids content, and that will cause clogging issues. And having the anode being close to the cathode, there is some crossover of oxygen from the cathode to the anode. So aerobic conditions appear at the anode surface, which are detrimental for MFC's operation. Then we want to treat wastewater. Wastewater has big volumes. What do? Do we just make a bigger sandwich to accommodate more volume? And can we do that? How can we do that? Scaling up electrons, making them bigger, introduces huge ohmic losses because these electrons now have to travel a long distance in order to be utilized. And in addition to that, the majority of electrodes in microbial fuel cell application are based on carbon textile material. So keeping the mechanical strength when they're so big, it also has been a challenge for many research groups. So MFCs has to be small. If we want to optimize them as electrochemical devices, they have to be small. They cannot be big. I mentioned you have to have a membrane in that sandwich structure. You have to have a membrane between the anode and the cathode. Membranes are really expensive, which makes MFCs cost prohibitive and not competitive to the other wastewater treatment technologies. And when these membranes are in contact with bacteria or wastewater, they're prone to very fast biofouling. We have to have an effective catalyst if we want to get more power. And unfortunately, the best catalyst when it comes to oxidation processes or reduction processes are gold and platinum, which are very expensive. That also adds up to the cost of MFCs, and they're not cost competitive. And as I mentioned, there are limitations, theoretical limitations of how much power can be produced by one fuel cell, regardless if it's just a fuel cell or microbial fuel cell, which is not enough to provide a sufficient power to power a fridge, let's say. So you need a multiple stack of those. Technically, you have to have multiple sandwiches or a big lunch. And there have been some research groups that managed to use that approach efficiently. So Bristol Robotics Lab in UK took that approach, having small microbial fuel cells, multiple in stacks, and they were treating urine to generate power and power the light bulbs in the toilets. They were successful in that adventure. Unfortunately, because of the small size of the MFCs, they are applicable in this case only for urine treatment. It cannot be applied for any other type of wastewater that has high TSS content because the small size will be prone to really fast clogging. So let's take a look at the other approach. What if we scale up microbial fuel cells as anaerobic digesters? And anaerobic digesters are big. They have to hold a lot of volume. The treatment, anaerobic treatment, usually takes from a couple of days to a month. So all this volume needs to be kept in there. They operate in a batch mode, which means that the water sits there for the duration of the treatment, and then it's replenished. So if we try to scale up microbial fuel cells like that, which means we have to make them big. And we are going back to these same challenges we discussed earlier. If you want to make microbial fuel cells big, then we have to make a big sandwich, right? So we have to scale up the electrodes, and we are seeing the same ohmic losses and the same mechanical strength issues. But let's say we managed to overcome that. Let's say we managed to build enormous anodes and cathodes, and we place those in a gigantic microbial fuel cell. Then these electrodes are so far away from each other that we are facing mass transfer limitations, which means that the amount of electricity that is going to be generated will be so small that it cannot drive the wastewater treatment fast enough as in other MFC's designs. And also, when we have one big microbial fuel cell, we can generate voltage theoretically up to 0.8 volts. We are not taking advantage of having a stack of fuel cells and increasing the power. Another aspect is that, as I mentioned, anaerobic digesters work in a batch mode. And that means that bacteria processing this wastewater, they release final products. And these final products actually cause inhibition effects. Bacteria sense them and they say, okay, stop, we work too much. Now we have to slow down. And that was the reason why for many years it was thought that MFCs cannot be used for high strength wastewater. They're applicable only for low strength wastewater because most lab studies tests have been done under batch operation. So what has Aquacycle done differently than other research groups? Why we managed to be successful in that scaling up process? And the reason is that we took that middle ground approach. We didn't scale up the technology only as an electrochemical device or only as a biotreatment process. We have a microbial fuel cell reactor that is the size of a standard car battery. So it's not small, but it's not big as well. That minimizes the clogging issues. The anode and the cathode are far away from each other that we can keep anaerobic zone around the anode. Then because the fuel cell is not big, we reduce the ohmic losses. We don't have these mass transfer limitations. And we managed to scale up the electrodes to an extent where we can still maintain mechanical stability and performance efficiency. We do not use a membrane, which eliminated the biofouling problem. It made the MFCs more cost-effective and reduced the ohmic losses that can be introduced by the presence of a membrane. We found a cost-effective catalyst to be applied that makes MFCs affordable and scalable. And as I mentioned, we managed to scale up the electrodes. We took a dual approach. So we scaled them up slightly, make them a little bigger, but at the same time, we use multiple units, let's say multiple anode units, to provide high surface area to volume ratio. At the same time, they're spaced apart from each other to minimize clogging issues, but still have high efficiency. We took similar approach for the cathodes. We have two cathodes on both sides of the microbial fuel cell to provide higher surface area. So, but one MFC cannot do all the magic, right? It's impossible that one reactor can remove all the organics from the wastewater. We have to have multiple of those. But to avoid this batch operation, we actually run microbial fuel cells in hydraulic series. We call them treatment trains. So the wastewater goes into the first MFC. It has been treated a little bit. Then the effluent from that first MFC goes into the second, treated a little more, and so on until we reach the effluent quality that is desired. So as I mentioned, these allow us to run the process under continuous mode, which means no inhibition. We are not accumulating these final products of the metabolic processes. And at the same time, we allow microbial communities to self-select in the different microbial fuel cells according to the wastewater composition at that point. And at the end, we take advantage of the modularity. We have multiple treatment trains that operate in parallel to increase the volume of the wastewater we can treat. And at the same time, that allows us to maintain the system easily. So we can maintain one treatment train while the rest of the system is still operational. And in summary, what has Aquacycle done differently? We optimize microbial fuel cells for wastewater treatment efficiency instead of energy recovery. We took advantage of the hydraulic series and treatment train design, or operating the system under continuous mode. And we have these parallel treatment trains to increase volume instead of having one big reactor. In addition to that, we provide real-time remote monitoring of the system performance and control.
So thank you, Sophia. Very informative. Now I'd like to just open up one more poll for everybody, just to understand where you are as far as your stage in terms of your interest in microbial fuel cells. So I'll go ahead and wait for a minute. And while I'm waiting, if you have any questions, go ahead and put them in the chat and in the Q&A, and we'll make sure to address the questions in the last 20 minutes. And if for some reason we don't get to, I'll follow up directly with each of you individually after if there are any questions we didn't get to. So now I'll go ahead and close the poll in 3, 2, 1, and I'll share that. And it looks like the majority of you say that your interest in microbial fuel cells is to stay up to date on trends in the industry. So great to hear that. And several of you also have active projects. A few of you are just researching. So thank you for that. Now I'll turn it over to Oriana Brechtker, and she can talk more about the applications where we've seen microbial fuel cells are best applied.
Great. Thanks very much. Thanks, Sophia. That was terrific. So I'm going to jump into more of the application specifics around MFCs, where they've been successfully deployed, where we could potentially address new applications in the future. And so what Aquacycle and others have found through various different pilot deployments and research opportunities is that really the best case scenario for microbial fuel cells right now is in food and beverage, and in those industries that are generating very high strength, so high organic concentrate wastewaters, but these are typically generated in lower volumes relative to the rest of their production environment. And I'll get into what that means in a minute. So food and beverage is a great place for MFCs to apply to begin, and there's been some successful implementations in beer and wine, as well as what we're doing in some of the other food and beverage industries as well. So the other sort of next steps for microbial fuel cells also can address some of the higher outputs in terms of concentration from pharmaceutical, personal care product synthesis, potentially into confined animal production, so manure management in the later stages of microbial fuel cell deployment. There's been several efforts with the military looking at how the technology can apply to forward operating bases and sanitation and water reuse management and deployment. And recently, some others have been also looking at how MFCs might apply in the oil and gas industry. Now, these are all sort of in development, right? We don't have, to our knowledge, commercial applications in many of these industries just yet. But as we start to grow the technology deployment through these industries, that ultimately reduces the cost of goods of manufacturing of microbial fuel cells as we start to scale up, which ultimately opens up new value propositions within these industries. Now, the largest market, as many of you I'm sure know, is in municipal wastewater treatment, right? Whether that's a centralized or decentralized approach, that is the biggest need. However, microbial fuel cells are unlikely to ever address a 300 million gallon a day centralized treatment plant, right? The extent of that application is massive, and there may be some opportunities for retrofits and things like that. However, within the stage of development so far, and how the technology is able to address really specifically different types of wastewaters and how the efficiencies change. We think the best case application in that industry is really going to be on the distributed side. So looking at replacements for septic and or small communities in terms of decentralized wastewater treatment and sanitation. But that's low strength, right? And still addressing a smaller volume than the larger centralized systems. And so, where the technology has been a good fit so far, has been focused in these areas where you've got really high soluble and insoluble biological oxygen demand, or BOD. So the insoluble, right, represents itself as total suspended solid, or TSS. But some of the challenges that conventional treatment technologies face are the same that microbial fuel cells face, right? Fats, oil, and grease. That becomes an issue when you've got anaerobic digestion or activated sludge or any membrane technology. And so fats, oil, and grease, or FOG, also is a challenge from microbial fuel cells, but we can tolerate up to around 300 milligrams per liter of FOG. That's higher than most conventional. You're still going to have challenges with MFCs across, extreme temperature ranges. There is more flexibility with MFC technology in that they can operate within a range of 10 degrees C up to 55 degrees C. So just, above freezing and up to some of the hotter temperatures, but you still need to bracket that temperature control. pH range is biological system, right? So you must stay within a pH range of between 5 and 9 for microbial fuel cells. It's a little bit wider than some of your other technologies, which will be very sensitive to a more neutral pH. But overall, right, these are some of the advantages that microbial fuel cells can bring in terms of a wider operational range on some of these areas. And at least with our systems, we can tolerate a much higher total suspended solid concentration, or TSS, than many other conventional technologies. So we've demonstrated successful degradation and treatment of wastewaters with TSS up to 35,000 milligrams per liter, and that's a direct feed. But as Sophia had mentioned, the treatment efficiency is really going to be dependent on what it is that you're treating. So not only the concentration of your organic compound coming in, but also the composition. And so when you're looking at biological oxygen demand, especially in the food and beverage industry, right, depending on what you're making, your composition of wastewater is going to be different. If you're confection, depending on where you are in confection, but largely that's going to be simple sugar, right? Sucrose and glucose. If you're in soft drinks, you're going to have sucrose, glucose, but you're also going to have artificial sweeteners. You're going to have some caffeine. You're going to have some other additives in there, which will increase the complexity. In snack food, right? You've got starches, you've got more compounds that require hydrolysis and fermentation, sugar refineries, just straight up sugar. But in breweries, which has been one of the first applications of microbial fuel cells, you actually see some of the most complex wastewater because what comes out, right? You've got you got some trace yeast, you've got some unfermented sugars, you've got hops, you've got potential residuals from grains, etc. And even though there's typically a solid separation step, you still have these trace elements. And during a fermentation with yeast, there's a lot of secondary metabolites that are involved, and that can occasionally be confounding to microbial fuel cells. And so the complexity of brewery wastewater is something that has challenged microbial fuel cells in the past. But we're not limited within these categories. In fact, we've tested a lot of different wastewaters from many different areas of food and beverage manufacturing, and even into pet food. But across the span, right, depending on the concentration of biological oxygen demand and the composition, you're going to see a varying treatment span, right, with the technology. Now, these are Aquacycl data, and it'll be different for others in the treatment arena that are commercializing microbial fuel cells. But we see some of the best efficiencies and the highest treatment rates when we're dealing with the highest concentrations of BOD and the lowest complexity, right? So that's a easy target. That's a value add where the technology can be a good fit. Where some other technologies, like even anaerobic digestion, high rate anaerobic digesters are typically limited on feeds around 50,000 milligrams per liter, right? And so we're well above that in terms of what we can take in an undiluted fashion and treat in a range of hours instead of days. And so how the technology really stacks up relative to others that are out there. And we borrowed this and did a modification from one of our colleagues. But when you're looking at biological oxygen demand in a range, right, you have the lower range of BOD, and this is generated from sewerage. So you've got municipal wastewater, which can come out in the higher range over here. And then you've got just some, trace organics that you might want to remove for a reuse application. And your best bet for reuse applications at the tail end, right, is always going to be a membrane-based technology right now. But as you start to increase in organic concentration, right, you start going up the scale, you're now more limited in the types of technologies that are out there that can address these wastewaters directly. There's high rate anaerobic digesters, there's the conventional anaerobic process, and then there's anaerobic membrane bioreactors, which are also a solution to address these higher ranges. But none of them, that to our knowledge yet, can address anything that's above 50 to 100,000 directly without some dilution or having to recycle multiple times through the reactor, right? So that extends your hydraulic residence time in total to be able to address these things, which means your footprint is going to be a lot bigger, your residence time will be bigger depending on the flows that you have to manage. But I will also say, right, on these high rate, these are high concentration, technology applications, you're never going to get drinking water out of these things, right? So no matter what technology you start with on this high end of the scale, what comes out still requires treatment with these other technologies paired on the back end, right? You still require some post-treatment, especially if you're talking about water reuse or zero liquid discharge, right? None of these technologies are going to produce an effluent quality that can go straight for reuse. And depending on what your reuse application is, you may want to be selecting different technologies or a combination of technologies for post-treatment. So where we really see the best fit for microbial fuel cells is as industrial pretreatment, right? Because we can take in these high concentrations and take the tough stuff first, right? We apply to situations where a producer may be hauling wastewater offsite because they either are not permitted to discharge to their sewer, or the sewer surcharges are so high when they do discharge that is cost prohibitive, right? So the alternative right now is just to truck it somewhere else. And so we can eliminate that, sit on site and treat that wastewater directly. And so either you're discharging to a POTW, to a sewer, or you're installing other technologies at the back end for a reuse application, right? But that is one of the first areas where MFCs can be a good application. The second, but less explored opportunity is really again, industrial pretreatment, but ahead of an anaerobic digester, right? So you have two anaerobic technologies complementing each other. And anaerobic digesters have been the workhorse, right, in industrial wastewater treatment for decades. And really the only solution that's been available and widely accepted for energy recovery as methane. But, you know, as if you have an anaerobic digester at a production facility that's been there for a few decades, right, it may be aging. Perhaps the production environment has changed and you're sending more concentration to it than when it was initially designed for. And so instead of having to rip that out and replace it, or adding new digesters or you know, reaction tanks to that system, you can deploy a microbial fuel cell ahead of it to help decrease some of the loading going in, but also actually change the composition of that carbon that moves into the digester. So not only does some of that carbon just, you know, get fully degraded into electricity, but that carbon composition becomes volatile fatty acid. And that volatile fatty acid, while kept within the right confines, can be a great feedstock for anaerobic digestion and actually increase the biogas production out of an existing bioreactor between 25 and 50%, depending on what it is you're starting with. So this is industrial pretreatment, but complementary to what is already out there to enhance energy recovery and health of an existing system. And so, you know, we talked a little bit about the future, and really, you know, there's still work to do, right? Microbial fuel cells are yet still just getting into the early stages of successful commercial deployments. And so the next step, you know, on the research side really is looking at, okay, how can microbial fuel cells now be applied cost effectively and commercially into synthesis and electrolysis, as Sophia discussed earlier. That's still very nascent. On the commercial deployment of microbial fuel cells that are out there now, the next stage is how can we really take advantage of the energy recovery capacity of these systems? We're not making methane, so this isn't a, you know, there's no cogeneration capacity that comes with these systems, but we are making direct DC power. Now, in order to harness that, that means you have to have a battery pack installed, right? You have to capture that energy, which is being recovered. You want to store it and then use it somewhere. But you're going to always have a loss if you're trying to convert from DC to AC usage, right? So best case scenario is that you're storing your DC power and using your DC power in charging stations, where that's charging a forklift or EV charging stations or LED lighting, you know, for example, in the warehouse facilities. And so we see those as the best first use cases for energy recovery from microbial fuel cells. And as capacities improve and as you know, MFCs are further optimized for this process, right? You maybe can branch out into more power and more useful energy recovery from MFCs. And of course, you know, there's been a lot of hype around microbial fuel cells over the last decade that hasn't really come to fruition. And so, you know, all of us in the industry are challenged to show those successful commercial applications. And so those are just starting now. And we look forward to sharing more about that in the coming months. But ultimately, just like with any new technology, the manufacturing costs have to reduce. There is a clear value proposition already in food and beverage, right? We can be cost effective relative to anaerobic digestion, relative to sewer discharge, surcharges in high surcharge rate areas, and cost effective relative to hauling costs in many areas. Not all areas, but many. And so there is the value proposition now. But as we're able to roll out, high volume manufacturing processes, et cetera, that reduces overall costs of production, which means there's new value add that's provided to the customer. And so scalability in terms of manufacturing is really the next stage to bringing down costs and then opening up new market applications. And one of the big focus points that we have is really in energy recovery, and the promise is real, right? When you're talking about the different workhorse treatment technologies that are out there, so aerobic activated sludge, we all know that's very energy intensive, right? You're not making any power with that. You're consuming a lot of it though. With anaerobic digestion, now this is conventional AD, you're talking about a longer hydraulic residence time, and you're making methane, and say you could either inject that for natural gas, or you're using it for cogeneration on site for electricity and heat. Well, per unit of organic that you remove, right? So say kilograms a day. If you compare these three technologies to a microbial fuel cell, or specifically Aquacycle's microbial fuel cell, you look at energy consumption. So you got a kilowatt hour per every kilogram of BOD that you treat, right? Of course, aerobic is really high. Anaerobic is pretty low, and microbial fuel cells through Aquacycle are even lower. We take advantage of gravity feed. We're a low pressure, low flow type of system. So we're not consuming much energy through the process, regardless of any energy that we might recover. And so, how that plays out in kilowatt hours per day, right? You've got a range of costs, and that's always based on a range of efficiency of your treatment technology. Now, in terms of how many kilowatt hours can we reasonably recover per kilogram of organic that we digest, right? Anaerobic digesters are usually in a range between 1 and 1.2. We've seen higher, we've seen lower. Aquacycle is right in that same range, right? And that's as DC power. But the challenge is, how do we usefully capture that and use it, right? And so there's battery storage, and there's distribution costs, et cetera. So what's important is identifying what the true value proposition is there, because there's a cost associated with all of that, and infrastructure cost, energy storage cost, and the project really has to justify whether or not that's deployed or not. And so, all in all, the power generated from these systems can be equivalent to what you see out of AD, but we're not just there yet, right? There's some infrastructure work that still needs to be done to make this a true value add to food and beverage or other applications. So let's talk a little bit about the myth versus the reality. Okay, so we talked a lot about scalability today, and the myth is microbial fuel cells are not scalable. Well, that's not true. I hope that you agree with us that that myth is busted. Microbial fuel cells can be scaled for commercial applications. However, the first applications are still going to be lower volume. We're talking 10,000, 20,000, 50,000 gallons a day, right? Lower volume, and a high concentration, right? Those concentrates that can be really problematic in food and beverage production or other production arenas. Those trucked off waste streams, right? Those really high surcharge waste streams. That's a great best fit for today. Tomorrow, right? Next year, there's going to be more opportunity, but for right now, that's the best case. Another myth, microbial fuel cells are a proven solution for energy recovery. No, that is not true. And hopefully we learned more about that today in terms of, energy recovery from fuel cells is still a very promising benefit, and it's measured. We know the power is out there, but it's discharged to ground right now. And so the next stage is, how do you harness that? How do you harness it cost effectively in your specific project? All right. The next myth is that microbial fuel cells can work for all wastewater applications. Well, in the research field, I would probably say that most wastewater that's generated globally has been tested by somebody in a microbial fuel cell lab. There has been a ton of research out there about different applications and specifically wastewater applications for microbial fuel cells. And there's some great results, but they're still all at the laboratory stage. And we have only a few commercial installations to point to. And so, no, it won't work for everything, right? Microbial fuel cells are not a silver bullet, and there's optimization that has to be done for every single unique application that's out there in wastewater. Not to say it can't happen, but as of today, right, there are specific niches where microbial fuel cells make sense and other areas where they just don't. And that's more a value-driven decision. All right, so we've busted a few myths and hopefully we've shared a bit of reality about microbial fuel cell technology and where it's at to date in its development stage, its commercial applications, and some of the best case usage areas for microbial fuel cell technology today. And so with that, I will still say that the future is bright for the technology, right? There's still work to do. But in terms of commercial deployments and the value that this technology can bring into wastewater treatment solutions providers, it's there, it's clear. It's not the silver bullet. But what's exciting is that, you know, the promise is still alive and there's still more to do. So with that, I think we'd like to jump into a little follow-up poll, and Julie's going to lead us off with that.
Yes, so thank you, Oriana, great presentation. And we've been getting a ton of comments and questions. So I'll just really quickly, I want to share the same poll that you guys had at the beginning. You know, what's your current perception of microbial fuel cells? And I'll just leave this open for a few minutes and then, or a few seconds, and then we'll go right into the questions. Okay, I'll close it in 4, 3, 2, 1. Okay. It looks like Oriana and Sophia, we have, you know, very similar. It looks like less people are saying they don't know much about them. So great. Glad to hear that you've done a good job educating. It sounds like, you know, great potential, but don't know how well they scale. Actually, I guess perhaps we, when we formed the question, we should have formed it a little bit differently because that could have been broken into two. So we'll see. I hope that you address the scale and cost effectiveness, but this is how the respondents responded. I'd like to jump right into questions because we do have a lot of questions, and we'll cover as many as possible. The first one is for you, Sophia, and it's a couple questions that I'm combining around the microbes themselves. And so does the selectivity of the microbial stack mean that a microbial fuel cell's performance will increase with time? And if yes, how long does it take to optimize itself? And is it important to have the right microbes, or do a whole range of them work?
So there is not a single microbe it's not a single strand microbe that works there. It's a microbial community, because when you start with the complex wastewater, there are many processes like hydrolysis, fermentation, and the final oxidation process, the diurnal surface, that need to happen simultaneously. So we have a consortium of microbial species. We usually source those out from nature, like lagoon sediment, for example. We seed the microbial fuel cells in our system and we allow them to self-select. So we operate the system in a specific way for a month to allow them to self-select. And these special microbes that can perform extracellular electron transfer from being like a minor population in the environment will become a dominant population in microbial fuel cells.
Okay. Another question that's maybe goes back to Oriana, some of your points. What is the single greatest challenge for the scale up of MFCs?
Single greatest challenge? I think for now, it's I guess the next challenge for us is going to be cost-effective energy recovery. And we've scaled up. It's reproducible. It's been proven, at least with our technology, across a few different application cases now. Our last webinar kind of addressed a few of those, and hopefully you'll see more in future webinars from us as well. But the scalability it's very modular. It's just, okay, what is it that you're wanting to treat? What's the quality of effluent that you need to achieve? And then what's the volume that needs to be processed per day, right? Those are the 3 questions that we need to answer before we can put together a cost proposal. Once we have those 3 answers, we can figure out, okay, how many modules, how many containers of what size need to be put on place to achieve that water quality and volume process on a daily basis. So I wouldn't say that that's a challenge anymore, but in terms of how can we best recover the power and make that a useful energy recovery process for the customer is the next stage, the next challenge.
Yeah, and I think I've gotten a couple questions around the energy production. So one is, will the MFC generate more electricity than a standard anaerobic digester to biogas to microturbine?
It'll be about the same. When you think about all of the different losses that happen in those 2 systems, right? In an anaerobic digester, you're making methane, which is usually a very slow process. You have to separate that methane through biogas purification. You capture that, you can burn it in the process of cogen or inject it for natural gas reuse, right? So all of those steps, there's losses. So, you're looking at a 30 to 40% efficiency recovery in terms of BOD to actual electricity reuse capacity. Microbial fuel cells offer roughly the same. And that's going to be really dependent on the amount of chemical energy that we're starting with, right? AD is successful because they're working on the higher range as well in terms of the biological content, the organic content that's coming in. And so MFCs are the same. If we're starting with a low chemical energy to begin with, we're not going to get much electricity out, right? We're starting with a lot of chemical energy, really high BOD stuff, we can get much more electricity out. But in terms of total recovery and efficiency, 30% is about as good as it's going to get. But that equates to different numbers in terms of kilowatt hours per day, depending on what you're starting with.
And so now translating this into maybe a higher level goal, how much would you say that the MFCs can help food processing plants reduce greenhouse gas emissions?
Sophia?
So as Oriana mentioned, it depends. It depends what is the BOD load, but based on our experience, we generate carbon dioxide. Of course, we do not generate methane, but carbon dioxide is 0.2% from the kilogram of BOD that has been fed into the system. If you compare to other wastewater treatment technologies like activated sludge or anaerobic digesters, we are 20% less. We produce 20% less GHG emissions than those technologies.
Okay, great. Another question, switching gears a little bit, is there a replacement time for an MFC? And if yes, what is the average time duration? So I imagine this question is about the life of the cell itself, the reactor itself. But could you also talk to the sludge removal? Because that, I think, is of interest to the audience as well.
Yeah, so longevity-wise, we've had systems working in the field, practically treating manure at a pig farm for over 5 years. We have not had to replace an anode. We have not had to reseed anything. We have not had to replace a cathode. We've replaced pumps. Those things always break. But in terms of longevity, right, this is a very self-sustaining system. As long as you give these bugs something to eat, the wastewater, and something to breathe, that anode surface, they're going to keep cranking. And so we've also challenged these systems in a lot of ways in terms of adding CIP chemicals. We've operated these things in real world environments where you're doing regular CIP clean in place procedures. You're gonna have bleach down the drain. You've got uneven flows, uneven concentrations, right? The system is quite robust in handling those things. In terms of replacement and maintenance, there's going to be some residual secondary biomass, right? Some sludge that builds up as a part of our service, because we operate strictly on a service model. We come in and we flush that out once a year or quarterly as needed. And then we discharge that whatever is required in that region. That's what's permissible. So, but in terms of like actual secondary biomass buildup, it's very, very low relative to anaerobic digestion and especially relative to aerobic processes. But the modularity of our design also helps us do this maintenance very easily. So the availability of the system is always 80% or more, which means when we're doing service, when we're taking out sludge, if we have to replace a component, whatever, you got 80 or 90% of the system that's still running while we do that, right? And we step through and we do our maintenance modularly through each system that's in play. So if something has to be serviced or repaired, the customer is never down. That system is always going to some fraction of volume availability.
Okay, we have a lot of questions that people have asked before and during, so we only have 3 more minutes. I'm going to take 2 questions. Oriana, let's talk about applications. A couple people have mentioned food waste anaerobic digester. Would this be a valid application? And another application, palm oil mill effluent, 35 to 50 metric tons per hour BOD, about 50,000 parts per minute. Would either of these be valid applications?
Probably not. So if we're talking about food waste, it depends on what kind of food waste we're talking about. So it has to flow, right? We need a liquid volume through there. We can handle high suspended solids, but there needs to be a flow. So we're not dealing with anything that is a solid matter, right? And there is obviously viscosity limits associated with that. So in the food waste application, it's something that we would need to look into, depending on where we are in that process. If it's liquid, like what's the suspended solid content, that's a maybe. With palm oil, fats, oils, and grease are a limitation for microbial fuel cells, just as they are for every other technology that's out there. And so it's a possibility, but we've never tried it, right? There's been no testing in palm oil in our specific systems. I think there's been some research done in different labs looking at that. It's a very challenging waste stream, and that's a big volume. And so likely not a great fit for where the technology is today.
Well, and I think it's good this goes back to your point about they're not a silver bullet. It doesn't work for all applications. Mm-hmm. And so thank you for your honesty and transparency. And the last question, we've gotten a couple people asking about the costs and how it affects the cost of treatment, as well as how it kind of compares cost-wise to traditional methods of wastewater treatment.
Again, it all depends on what it is that you're treating. So on the high range, which is where the technology is a good fit, I'm talking high range of concentration. And most environmental engineers always think about loading, right? And loading is the combination of concentration and volume. But the reality is you can have an equivalent load with really high concentration and really low volume versus really high volume and low concentration, that it can equate to the same load. So it's really important to separate these two things when you're talking about microbial fuel cell technology specifically. We deal with high concentration, low volume, and that's really what we're good at dealing with. Now, when you compare the cost of treating really high concentrates, what microbial fuel cells can do versus anaerobic digestion, which is going to be your only other option, it's also going to stack up relative to your regional operating area, right? So we can usually offer a much smaller footprint. So that means lower equipment cost and much faster processing time. So we're going to take those concentrates and we're going to take out 90% of that in a 13 to 18 hour residence time, as opposed to needing multiple 10-hour batches to process through. So your initial investment will be much lower. The OpEx is going to be typically lower than what you would want to pay to a sewer, right? But there is a range, and I can't say it's one price per gallon. I can't say it's one price per pound BOD, because it's not. It's all very project specific, depending on what we're starting with and the quality that's required and the amount of equipment that we need to install to make it happen for the customer. But I can tell you, relative to high surcharge areas and relative to hauling, which are the two use cases which we're most accessible to, that we're usually 20% to 60% lower than the alternative.
Okay, well, great. And with that, I'd like to close this discussion. I think that it's been very informative, very engaging. Anybody who didn't get their questions answered, I'll follow up directly with you, and hopefully, answer whatever questions didn't make it. I'd like to thank everybody for joining, and thank you, Oriana and Sophia. I'll also send out a copy of the recording. So I know there's a lot of information presented, a lot of content, and you can go back and rewatch it and learn more. So thank you, everybody, for joining, and goodbye. Have a great afternoon, evening, or morning.